In this video, I'm going to solve several triangles using the law of sines, including one instance of the ambiguous case of the law of sines. Okay, I remind you that this is the method whereby we determine how many solutions that a triangle has if we're given two of the sides and one angle that's not included. So the first thing I will do is look at my angle, 65 degrees. That's less than 90, so I know this is the first case. Here's case 1. Once you determine if it's case 1 or case 2, you have to ask, is A greater than B or less than B? I did that for case 1 and for case 2. In our situation, since A is less than B, we're going to further ask how it compares to B sine A. Again, A is less than B. Now we have to ask, how does it compare to B sine A? Well, in this situation, B sine A is 20 sine 65. So let's see what that's approximately equal to. Use the calculator for that. 20 sine 65. It's about 18.1. Okay, and clearly 15 is smaller than that, so I have A is less than B sine A. In that situation, there are no triangles that actually meet this description. Okay, so that's it. It says solve for any possible triangles. Because there are no possible triangles, there's nothing to solve. We're done. All right, let's try this situation. Okay, since A is equal to 90, this is case 2. Again, we have to ask ourselves next, how does small a compare to small b? And in this situation, A is greater than B. So my notes are going to tell me that there's one possible triangle when A is greater than 90 or equal to 90, and A is greater than B, one possible triangle. So let's solve it. Again, we'll use the law of sines. We're only going to use the part that deals with the A's and the B's. So I've got little a over the sine of angle A equals little b over the sine of angle B. I should point out this is just a right triangle. We could use Pythagorean theorem and right triangle tree, but we'll use the law of sines. Okay, to solve for b, I need to cross multiply. 25 sine b equals 20 sine 90. And from here, I need to first get rid of the 25. I'll do that by dividing. That'll cancel. After which, I will get rid of this sign by taking the inverse sign. Do the inverse sign of 20 sine 90 over 25. Again, we use the calculator for this. Inverse sine of 20 sine 90. Close the parentheses over 25. It's about 53.1 degrees. Okay, now solve for any possible triangles means we need to know what little c and big C are as well. Well, we've got both of the other angles, so now it's quite easy to find angle C. It's simply going to be well, I remind you that all three angles are going to add up to 180. So from that, I'll subtract angle A, and I'll subtract our approximation for angle B. 180 minus 90 is 90, minus 53.1 is 36.9. So we have an approximation for the third angle, and now all that remains is to find side C. Again, we'll use the law of sines. A over sine A equals C, which we don't yet know, over the sine of 36.9. This situation is much easier to find the missing side. All we have to do is multiply by the denominator. C is equal to 25 over sine of 90 times the sine of 36.9. Sine 36.9 divided by sine of 90. It's approximately equal to 15. If I use Pythagorean theorem, we'd find that it's actually exactly equal to 15. Okay, one final example. All right, let's first consider how many triangles we're going to solve for. Okay, because A is 65, I know that because it's less than 90, it's case 1. Now I have to ask, is it greater or less than B, or is small a? small a is less than b, so this is going to be one of those situations where I have to compare it to b sine a, right? If a is less than, if a is less than 90, sine a is less than b, I have to compare it to b sine a. Now, in this problem, b and angle a are the same. We figured out b sine a is approximately 18.1. Again, b sine a, it's the same one we did earlier. It's approximately 18.1. Last time our little a was 15, which was smaller. This time it's 19, which is actually greater. A is greater than b sine a, and therefore we actually have two triangles. This is the ambiguous case. So let's go ahead. We're going to use the law of sines, and we're going to solve for angle b. All right, a over sine a equals b, which is 20, over the sine of angle b. All right, to solve, again, we're going to cross multiply. 19 sine b equals 20 sine 65. And from here, I will divide by 19. So they cancel. And I'll take the inverse sine of both sides. So b should be approximately equal to the inverse sine of 20 sine 65 divided by 19, which is approximately, a lot of approximations going on. The inverse sine of 20, close, oh, I'm sorry, not closed yet, 20 sine 65, now we close, divided by 19, close again. It's about 72.6. Okay, hopefully you're wondering, when are we going to stumble upon this second triangle, right? And the answer is, as soon as we find our first angle. Angle B is not the only angle that has this sign. In fact, I want to go ahead and approximate that. 20 sine 65 divided by 19. 0.954. So when we took the inverse sine of this, we were asking the calculator, what angle has a sine of 0.954? And the calculator said a 72.6 degree angle. The interesting thing here is that 72.6 is not the only angle that has this sign. And I've got a GeoGebra file that's going to demonstrate that. If you look at a 45 degree angle, its sine's about 0.71, but you'll notice on the other side of the unit circle, we also have an angle whose sine is 0.71, and that is the angle that's 135. So if I change this to 7, we said 72.6, I believe. I can change it to 73. 73. It has a sine of 0.96. Let's check that one more time. It should have a sine of 0.954. Yes. Oh, 0.96. So it's very close. We'll assume that 72.6 would be 0.954. We'll notice on the exact opposite side, we have the same sign. Now, the relationship between these two angles is fairly easy. You'll notice that they're supplementary to each other. They add to 180. That's what I've added to our notes, actually. You might have noticed that earlier. And the ambiguous case, if you wish to find the second angle B, you simply subtract the first one from 180. So let's go forward to our problem. So I've got this angle here. We're going to call it B1. That has a sine of 72.6. Has a sine of 0.954. To find the other one, we'll call it B2. All we're going to do is subtract B1 from 180. Okay, that's approximately. Well, the 180 is 180, and B1 is approximately 72.6. So that would mean this angle is 107.4. We'll call it B2. All right, so we've got angle B1, angle B2. These are different triangles. This was the first triangle. This is the second triangle. Again, it was an ambiguous case, so it leads to two triangles. What we're missing still are all the C's. So we'll go back to B1. We'll go ahead and finish this part of the problem. To find angle C1, I'm going to need to take 180 and subtract A and B1. So it's going to be approximately equal to 100 minus 65 minus 72.6. That's going to put C1 at, let's see, We're subtracting 137.6, so it should be 42.4. If we wish to find side C, we're going to have to use the law of sines again. A over sine A equals C, which we don't know, over the sine of 42.4. To solve for C, we simply multiply both sides by 42.4. So I've got 19 divided by sine of 65. That's what the left side is. I have to multiply it by the denominator, sine of 42.4. C is about 14.1. Okay? And that's the first triangle. We used the A, the B, and the A that they gave us up here, but we also, to round out the information for the triangle, we found angle B, we found angle C, and we have found side C. Those are the three. Okay, but we can also solve another way. I've got B2. To find C2, I'll need to subtract, again, they all add up to 180. I'll subtract A, and I'll subtract B. Okay, that leaves us with a very small angle, 115. It's going to be 7.6 degrees. All right, and then, again, to find side C, we'll need to use the law of sines one more time. A over sine A equals C over sine C. To solve for C, again, we'll use the calculator. The left side is still 19 over 65, sine 65, and this time we're going to multiply it not by the sine of 42, but by the sine of 7.6. Let's see what we get. It's about 2.8. So we solved two triangles. I'm going to call this guy C2. We've solved two triangles. That was the ambiguous case.